Hello, folks. My name is Ivan. I work at Microsoft as a dev manager. And today it is my pleasure to introduce to you to a 20-year journey of a product called Cosmos Analytics. I hope that some of the things that I share will be useful for you on your own journey and on the products that you do own. I'm not going to go talk about each and every feature that you see here because there's just too much. Each one of those will take a full presentation, but I want to explain what we did. And I want to start with what is it that we're about. We are the big data solution for Microsoft. We enable our customers to deal with all sorts of sizes of data. We have, up to 40 exabytes of data that we handle every week. We churn about 7 exabytes of that, and people do all sorts of stuff with this. They work with, interactive and batch and machine learning and streaming and all sorts of different things on this system. If you look into who uses this on Microsoft, you're going to find out that pretty much every major Microsoft product uses this, from Azure billing to Xbox player reputation or rankings to Office feature profiles to Windows updates. So every time Windows is rolling that out on the second Tuesday of the month, they're tracking the progress of this and compatibility of devices using my product. It is a mission critical system for Microsoft, and it's something that's been like that for the past 15 years at least. I cannot really go over all the details, but one of the things that I want to highlight is that this system is designed from the bottoms up as an integrated stack. It starts with the design of the data center all the way down to the concrete and how air flows and cooling and power and whatnot. It goes into the fabric, it goes into the federated platform that gives me my containers, all the way into what is the traditional software stack. Be that the store, be that job services, compilation, front ends, and the analytics engines, which is where we're going to spend some more time this time around. All right, so what I'm going to do here is I'm going to open a project that I'm actually working. This is a real thing I'm doing. And what this demo is about is, what this job is about is to figure out how much data is written or read by Vertex over days. For this demo, I'm doing 3 days, but typically I query an entire year. So let me show you what a scope script looks like. They are all similar. They start with something that we call extraction, and this is the thing that does the normalization of data. You can see here that I'm using a function. This function will take, the inputs that are going to be running and normalize that into a row set. I'll show you the inputs in a second, but let me go over the flow here. Extractions, and then once I extract, I have a named row set, and this row set can be queried. And this thing looks like pretty much every other query engine you're going to find anywhere, with a few distinctions. Like one of the distinctions is you can see this function right here. And the thing that might be no obvious is what I could do is right here, do C# and start writing C# code. I kind of prefer to do this slightly differently. I want to open my solution here, and you can see that that function is actually implemented right here. And this is me trying to get my data broken in the boundary of days, right? So I'm taking the daytime and doing some manipulation here. But essentially, you can do anything you want. This is entirely extensible. It's free code. It could be C# like I did, or it could be Python. So then in the end of the script, we do multiple outputs. So extraction, processing in many different ways, and you can do multiple outputs at the end. Now, there's a very interesting thing about this. So I'm doing extraction from somewhere. So what I want to show you is what somewhere is. You can come here and see the URI, and you're going to see this weird syntax. There's kind of a relative path, and then you have a template for a number, and then there's a start and end dates and whatnot. Let me show you what the thing is. I'm going to open the store browser. Those are files on the store. And you can see some of the files that I'm querying, they're here. And you can see they're like fairly large files, and there are multiple of them. And I'm querying this over multiple days. You can see on the URI over here, this is January 25th this year. And on my script, I'm actually querying multiple different days that I'm defining here, from 23rd to 25. Now, what the magic of this thing does is to make this look like one massive file. So virtually, the system is like creating this as one file, and you don't have to deal with opening them separately and doing all sorts of editing and error handling and whatnot. The system will do this for you. So the first thing I'm going to do is I'm hitting F5 over here, and I'm starting a compilation. And we're going to see in a moment what this compilation does, but I'm going to give you like a brief preview. It's looking to my inputs and sizes and how many machines I have to run this thing. And it's going to go and generate some code, and it's going to be an actual exe. I talk a little bit more about that. Not much, but a little bit. And then once the exe is ready, which takes about 20 some 30 seconds, this thing is going to run it. So this is what the optimizer thinks I can do in parallel. This is what we call stages. And we're going to go and split this like this. I have just my machine. So this is a very simple plan, right? I don't have a lot to do. There's some limits here, at most 4 containers, and that's it. Okay, so what you're gonna see now is this thing is gonna actually run. And if you look at the background, you can see all the bells and whistles that you get to Visual Studio. You can step through, you can put breakpoints, you can, see the code that I'm running, you can do all the stuff locally. Okay, so again, this is for my machine. But just for your benefit, because I'm a fun guy, I actually went out and run this job on the cluster before. So this is the job, and you can see the plan here. You can see all sorts of information. I'm saying use at most like 110 tokens and whatnot. I'm going to go back here, and I want to take a look at what that job was. So I did a job view, and this is downloading from the cluster. And I'm going to show some more advanced things. So we're going to download some additional things. So you can see on this job, when I run on the cluster over real data as opposed of sample data, it ran for 43 minutes. But it actually consumed 20 hours of computation on the cluster. And compilation was like, 40 some seconds. When you look down here, it parsed 4.7 terabytes of data. And then it wrote about 1.5 terabytes. Now, if I go into this graph here, the first thing is I can actually, if I were submitting this live, I could see the job progressing just like this. But because I'm taking something that finished, you can see the playback as it goes. So let me zoom in here, and I want to show something fun for you. So the extraction phase, which is that normalization, I end up running 3,700 tasks on this over, almost those 100 some containers. So there's some serialization, there's some of the stuff is done in parallel. But it's kind of interesting. Despite the fact that I have like this one virtual massive file, we know how to do data parallelism. And then that function that we wrote, the event extractor, now behaves as a parallel extraction algorithm because we coordinate the work via the job manager, which I'm going to talk a little bit more. So you can see there's parallelism on the data, there's parallelism on stages that I can do it differently. And here's the fun stuff. There's a lot of stuff to show here. I'm going to click on the vertex execution view, and this shows you every single container that run. You can see the entire thing here and the timeline. I can click on a container, I can download the container, I can look at things like critical path. So now I can go out and see I have some failures, I have some things that I kind of like run in parallel and peak the faster. And I can, come into this and say, I want to know why something failed and download. So, okay, this was very simple. All right, let me get a more interesting one for you. So let's try this. So you can see exactly what we're doing. Extraction, some aggregation across racks. You can see the inputs, you can see the fields. There are entire data flow analysis here. The other thing that you can do with something like this is, if I go back on the job, let me find the thing. Here it is. I can go back on this thing and I can look at diagnostics. And as this run, we actually look into the execution and we figure out what is it that you can do to make this better. One of the things that is interesting you can see is you can look how I use your containers. So you can see a lot of parallelism in the beginning and a couple bottlenecks. So I know I can do a much better job on this particular script, right? But again, super straightforward script. This is what I'm doing. I just want to go fast, and I rely on the optimizer and all the smarts on the platform to make this easy for me. So what you see on the slide is kind of like a little bit of the details of what the demo is doing. So if you start on the boxes, you can see on the first box there's a compiler front end. The compiler front end will take and do the parsing of the scope job and all the user custom code, like you saw, my functions or Python code or whatnot. And we will produce an abstract syntax tree using Roslyn, which is the C# language. So this is formally defined and open source. Then that is fed into our optimizer, and that's what you see on the second box. this optimizer will go and take a look into my inputs, and we're going to decide how much parallelism I can have. After this is fed into the third box that you see on the top, which is CodeGen, where we generate an exe out of the stages. And this exe uses a bunch of like libraries for distributed sorts or distributed merges or distributed hashes and whatnot, right? There's a whole full library here. The result of this, the binaries are saved on the store, and we enter request on the first blue box on the top line over there, which is the job queue. The job queue will spawn a job manager, which is the first process out of something running, a job running on the cluster. I'm going to talk a little bit more about this and how that works. But this job manager is the brains of any one individual job. It looks into things like scheduling the containers, obeying the quota that was given for the job. It will handle errors, will handle things that fail, will look at things that are running slow and try to do things in parallel or trying to have alternative containers and whatnot. It talks to the resource manager, Yarn, to get containers for each one of the tasks, and then it babysits those tasks and takes care, make sure that they're working, and progresses over the stages and the tasks, either dependencies are satisfied. In the end, it publishes a bunch of events. It tells us about what the job did, and concatenate the outputs that the consumer can then take that output and use somewhere else. Now, one of the things that I want to highlight here is the optimizer. So the optimizer looks at some of the things that I talked about, the file sizes and the file locations and all the different ways to combine operators, hash joins, right? I can do, when I do a hash, I can sort the data in a hash, or I can, basically hash the data, then sort and do some other stages, right? All the choices, all the trade-offs. But we also have the system that is offline that will track recurring jobs over time and will collect information. So you can see the first line over here has a compiler and the optimizer and the scheduler, and it has the runtime and the CodeGen that you saw on the previous slides. But you have this parallel thing on the bottom where we're using all sorts of different techniques to learn about your job and then use that for the next time we go and execute. The next stage over here is like those little boxes at the bottom of the first slide is really the yarn++. And this is our federated container allocation and is also the DC Fabric gateway for us. It stays between the jobs running and the data center. And what this thing is yarn that we had to augment. Our clusters are in the order of 50,000 machines per cluster. The old yarn was able to do like 4,000. So we kind of like worked through with the open source community and we put it back in there. You can see what we did to let this thing scale via federation to up to 50, 60, 70,000 machines, which is where we need this to be. We also added the notion of speculative execution or opportunistic container into the open source so we can keep our utilization high by opportunistically finding things that are idle and giving jobs more than what their quota will grant them. There's a set of like very interesting other features here, but I want to point out the scale of this thing. Like we actually run 10,000 containers per second on the system today and about 90,000 container tasks per second. So we kind of reuse the container as well as a performance guarantee. So let's go back into the same view that I saw on the first slide, but now let me show what the control flow is. And you can follow the numbers. So number one is me submitting my job. And when you go look into the number two, that is the job service. It will invoke the compiler service that will produce my binaries, and we'll also query the store to figure out where the data is and how the inputs are, sizes, locations, how they're split. Then there's a little fuzzy thing. There's a router in a cloud over there. I'm going to detail that a little bit more. And the job service will call the resource manager to spawn a container for the job manager. When the job manager starts, it will do the same thing again, but to spawn containers for tasks. But if you look at this, you can see that on the machine itself, we have a node manager with two queues. And this is a way we found to protect the machine. That's on the bottom extent node. We call extent node because we actually save the data on the same place where we're doing the compute. So we try to push the code where the compute is. And we use those queues to make sure that if we have a hotspot on scheduling or any other problem on the cluster, the machine itself has a way to hold back the workload. So that little cloud, right, is this thing here, is the router service. And the allocation manager and the router service are the things that allow me to actually talk to multiple yarn subclusters. We're using Hadoop 3, so each one of those days can take up to 10,000 machines, but we still need way more machines than this for our applications. I have jobs of up to 3.5 million containers running at the same time. So, I need tens of thousands of machines to be able to run this thing. And so this is how we scale. Now, this is the other thing that this Yarn++ can do. It can do subcluster coloring. So because we're using a federated hierarchical thing here, what I can do is I can take some subclusters and then put applications there that require more isolation. For instance, we have a streaming version of this that is very latency sensitive. And what we do is we kind of have dedicated clusters for them. I could do this for anything, IO intensive things, CPU intensive things, and it's all fully integrated into the Yarn++. The other thing that we have is the other side of this platform. And the other side of this platform is the integration with the data center fabric. When you have massive data centers like this, there's always something wrong going on. I worked in places before where we had water leaks in pipes. We had rooms so big that the water condensed and it rained inside the data center. There's some very unexpected things when you get to the scale. And even on a normal data center, there's always something going on. You need to do maintenance on the generator. You need to do maintenance on the switches, the network fabric. You need to do power, cooling. Everything is going wrong at the same time. And even when nothing's going wrong, there's scheduled maintenances you have to do all the time. So we kind of have this gateway between the DC fabric and the federated platform where we coordinate the vacation of fault domains and upgrade domains. This is something that I worked before, and it's used in all the Azure documentation. So if you ever use Azure, it's a similar system. That system is based on this system. So the Cosmos Analytics thing is actually older than anything Azure has. So what is the summary of this presentation? We have this system called Cosmos Analytics. It is mission critical for Microsoft. It's been for 15 years. It's very developer friendly. I hope you liked the demo. I highlighted just 5% of what we have there, but I hope you can see how our developers will like this platform because it solves very pragmatic things for them. It's very feature rich. It abstracts away all sorts of things that we would otherwise have to handle. It scales immensely. So, I can work with phenomenally big virtual files. And it has a very high tolerance to failures. Most of the time, you don't even know something went wrong. The system will balance, will compensate. It scales, and it's very cheap. We tried pretty much every analytics engine there is on the market. This thing was cheaper than everything else. So fully integrated design. So what we have here, all right. So this is why I'm here. We're always hiring. It's a very interesting problem space to work, and also I love to have feedback on what to do next. Some people say, hey, I don't want to learn scope. Let me write Python. And then you generate the job out of Python, right? So we're working on that. Should we be open sourcing? Should I be supporting Linux? Machine learning libraries and whatnot, a lot of them don't work on Windows. So we're looking into running this on Linux as well. So feel free to reach out to me. There's my email at the bottom. If you're interested, you think we should open source this, send me a note. And thank you. I hope this presentation was fun. I hope the demo was useful. And have a fantastic day. Thank you.